Okay, good morning, everyone. Okay, we'll pick up on the Hello? Hello? Okay, we'll pick up on the subject of amines. Okay, I'm going to share my screen and all right, amines are organic nitrogen compounds, and if we start with ammonia and we replace one or more of the hydrogens, then we have either a primary, secondary, or tertiary amine, depending on how many we replace. These are all what we call aliphatic amines, where we have a saturated hydrocarbon group. These are aromatic amines, where the nitrogen is directly attached to a benzene ring or other aromatic ring. And then these are heterocyclic amines, where the nitrogen is part of a ring. Okay, in the case of pyrrole and pyridine, these two amines are both heterocyclic and aromatic. Okay, these are just heterocyclic and aliphatic. Okay, these don't meet the requirements for aromaticity. There's no continuous conjugation. In fact, there's no conjugation around the ring. Okay, I'm going to show you this again. These are some naturally occurring amines. These are called alkaloids. Coenine from hemlock, nicotine from tobacco, and cocaine from the coca plant. In the IUPAC, we take the name of the longest carbon chain, and we drop the E, and we add the suffix amine. Okay, so this becomes 2-butanamine. You could also say butan-2-amine. That's the more recent version. And here the parent compound is ethane. We consider ethane to be more substituted. So benzene ring as a substituent is a phenyl. So 1-phenylethanamine, and this is the S configuration. This is hexane, 1,6-hexane diamine. Okay, these are anilines. If aniline is the parent compound, then the amino group is automatically on carbon number 1. The amino group is actually a group that has a low priority when it comes to naming of functional groups. Okay, here the alcohol takes priority. So this is ethanol, it's 2-amino ethanol. And here the carboxylic acid group takes priority. The carboxylic acid group is way up at the top as far as functional group naming priorities. Common names, once again, we can name the alkyl or aryl groups that connect to the nitrogen and then the word amine. So methylamine, tertbutylamine. This last one would be triethylamine. This is dicyclopentylamine. Okay, so we just name the groups that are attached to the nitrogen. That's the common name. Common names are widely used commercially still in the United States. Okay, it is possible for nitrogen to have, and it is common for nitrogen to have 4 bonds. And if it does, it's called a quaternary salt. It's a salt because the nitrogen now has a plus charge, and there needs to be some anion that's associated with that cation. Okay, so this is tetramethyl ammonium chloride. We've got 4 methyl groups. Hexadecyl pyridinium chloride. Hexadecyl is 16. This is pyridine. Okay, nitrogen with 4 bonds has a plus charge. Okay, and then earlier we had a phenyl. If it's a benzene and a CH2, that's a benzyl. So this is benzyl trimethyl, there's 3 methyl, ammonium hydroxide. All right, amines are polar compounds. Okay, nitrogen is has a high electronegativity, but not as large as oxygen. So nitrogen does exhibit hydrogen bonding, but the hydrogen bonds are weaker than OH hydrogen bonds. And that's illustrated in the difference in boiling points between methylamine and methanol. Okay, these actually have similar molecular weights, okay, 31.1, 32. But because the hydrogen bonding, the strength of the hydrogen bonding is so different, there's a significant difference in boiling points. Okay, methanol is a liquid at room temperature. It boils at 65 Celsius. Methylamine is a gas. It boils at negative 6.3. Okay, this is one of the most important things I want you to remember from this chapter, and that is amines are basic. They are weak bases. And just like ammonia, aqueous solutions of amines are basic. They'll produce small quantities of hydroxide ions. All right, the equilibrium constant for this reaction is products over reactants. Okay, but we leave out pure liquids and pure solids, so we omit the water here in the denominator term. And that makes it that would be the Kb without the water. If we look at the reverse reaction, okay, the conjugate acid, if we make a solution of the conjugate acid in water, okay, that produces a few hydronium ions, and so the solution is now acidic, but not strongly acidic. Okay, so we can quantify the acidity by using the Ka. Okay, this is the reverse of what we saw on the previous page. The Ka value for the methyl ammonium ion is 2.29 times 10 to the minus 11. So the pKa is 10.64. Okay, not a very large number. For any conjugate acid-base pair, okay, if we take pKa plus pKb, that equals pKw, which is 14. And so if we take 14 minus 10.64, okay, that gives us the Kb of the conjugate base, okay, which would be 3.36. All right, so we can predict using Ka and Kb values, the position of equilibrium. So if we take methylamine and acetic acid, acetic acid is a weak acid, methylamine is a weak base. Okay, this will go to products because we're producing a weaker acid. A larger pKa means a weaker acid. Okay, so the position of equilibrium lies to the right. Okay, the print's a little small here. Aliphatic amines have about the same base strength, no matter what the R group is, about 3 to 4, and are slightly stronger bases than ammonia. Okay, so ammonia here is up at the top for reference, 4.74. Methylamine, 3.36. So that is a difference of a little more than 1. So this is more than 10 times more basic than ammonia. Okay, putting other ethyl groups on there doesn't change the pKb much. Okay, we have an ethyl or a cyclohexyl. Okay, not much difference in the pKb. Secondary amines, there's a slight decrease in the pKb, so a slight increase in basicity. With tertiary amines, okay, there's actually in some cases there's not much change. There's some other factors involved, including solvation. Tertiary amines are less solvated in water. They're less surrounded by water molecules. Okay, let's look at aniline. Okay, aniline has a pKb of 9.37. Okay, so that's a difference compared to methylamine. That's a difference of about 6. Okay, so that means aniline is a million times weaker. Okay, that has something to do with the benzene ring, which we'll talk about, and resonance. Okay, in the case of 4-methyl-aniline, what's happening here is the methyl is pushing electrons into the ring through the sigma bonds. Okay, and so that gives us nitrogen a better chance of donating to an acid. So there's a slight increase in basicity. The pKb is a little bit lower. If we have electron withdrawing groups, okay, such as the nitro group, okay, that gives us a weaker base. Okay, so 4-nitroaniline is more than 1,000 times weaker than aniline. Okay, and then heterocyclic amines. Okay, we have pyridine and imidazole. Okay, these are also weakly basic. Okay, much weaker than aliphatic amines. Okay, in the case of imidazole, there's 2 nitrogens, and the nitrogen that's more basic is this one without the hydrogen. Okay, these are the pKa's of the conjugate acids. Okay, and if you take any one of these, you add them together, you get 14. Okay, so why is aniline a much weaker base? Okay, so here's a comparison of cyclohexylamine and aniline. Okay, cyclohexylamine picks up a proton from water to become the cyclohexylammonium ion. pKb is 3.34. Okay, for aniline, it's 9.37, so again, that's about a million times weaker as a base, 6 ppb units. Okay, here's the reason. Okay, amines are basic because of that lone pair. Nitrogen uses that lone pair to donate to a proton. And you can see because of resonance, in several of these resonance structures, that lone pair is not available for donation. Okay, we've got 3 resonance structures that have no lone pair on the nitrogen. In fact, there's a plus charge. And so, so that lone pair is not available, not as available to donate to a proton. In the case of cyclohexylamine, there's no resonance structures. The lone pair is not delocalized. It doesn't go anywhere. It's on the nitrogen. That's where it stays. Okay, if we have an electron withdrawing group, such as a nitro group, especially at the ortho or para positions, you can see that the nitro group, through resonance and also through inductive effects, significantly reduces the availability of that lone pair on the nitrogen. Okay, so select the stronger base in each pair of amines. Okay, this one is called morpholone. It is the stronger base, and the reason is here is not resonance, but it has to do with hybridization. Nitrogens that are sp2 hybridized, that is trigonal planar geometry, okay, are going to be less basic than those that are sp3 hybridized. Okay, so the reason is hybridization. So morpholone is a stronger base. Okay, here, part B, this is 2-methylaniline, and then we have benzylamine. Okay, so benzylamine will be the stronger base. Okay, there's no resonance structures that involve the lone pair on the nitrogen. You have resonance structures with the benzene ring, but they have no effect on the nitrogen. Okay, so the lone pair is much more available to donate to a proton. Okay, here, again, that lone pair is going to be delocalized by resonance and much less available, okay, just like as shown here. Okay, we saw that in the case of aniline, resonance greatly reduces the basicity. In the case of this base called guanidine, this is one of the strongest bases among neutral organic compounds. It has a ppb of 0.4. Okay, so it is about 1,000 times more basic, say, than methylamine, 3.36. Okay, in this case, resonance actually makes it a stronger base. Okay, so here's guanidine. And if we protonate this nitrogen that's doubly bonded, okay, this nitrogen up at the top picks up a proton. Okay, this ion now is resonance stabilized. We can spread that plus charge over all 3 nitrogen atoms. Okay, we push from a lone pair of electrons. We move electrons toward a positive charge. Okay, so this is an equivalent structure. Double bond and the plus charge are just in a different place. Same way with this one. Okay, by spreading around that positive charge, the conjugate acid is much more stabilized. Right, all amines, whether soluble or insoluble in water, react quantitatively with strong acids to form water-soluble salts. Okay, so here we have R-norepinephrine. It's only slightly soluble in water. It has a couple polar groups. These OHs, this alcohol, the amine, only slightly soluble in water. Okay, but when the nitrogen picks up an H, say from a strong acid such as HCl, we get the hydrochloride salt, which is now much more water soluble. Okay, so this section deals with synthesis of primary amines. Most primary aromatic amines are synthesized first by nitration of an aromatic ring, followed by reduction of the nitro group. Okay, you might recall from the previous chapter we looked at all those different reactions for introducing groups onto a ring. We didn't have a method for introducing an amino group onto the ring. And so what we typically do is we'll nitrate and then we'll reduce. You can reduce by hydrogenation. You can also use an active metal. Right, besides bases, amines act as nucleophiles. That is, they can use that lone pair to attack a carbon atom. Okay, so this is an SN2 reaction. Nitrogen attacks a carbon, kicks out a chloride. We get a hydrochloride salt. Okay, there's one more carbon group attached to the nitrogen now. If there is an excess of amine, then we have another acid-base reaction that takes place. Okay, so if we have unreacted starting material, okay, this can pick up a proton. We get the neutral secondary amine in this case, and then a primary amine salt. Okay, in the second step, a new secondary amine was produced, which can then act as a nucleophile. And so the result is the final reaction mixture will consist of varying ratios of primary, secondary, tertiary, and even quaternary salts. Okay, these ratios are difficult to control, and therefore we avoid using amines as nucleophiles in nucleophilic substitutions. Okay, a couple of exceptions. If we want a quaternary salt, then we would use we could use a large excess of the alkyl amine. Okay, that would drive it all the way to the quaternary. We could also use a large excess of ammonia to get a primary amine. But generally, this is not a good synthetic method. Okay, what they're saying is that, okay, once we get this secondary amine can then attack another alkyl chloride to give us a tertiary amine, and it keeps going. And we'll end up with a mixture of products. Okay, want to make a couple of other comments about the basicity of amines. Okay, first of all, amines, low molecular weight amines, many of them have a characteristic strong fishy odor. And when fish spoil, they give off low molecular weight amines. And this gives rise to the characteristic odor. Okay, things like methylamine and ethylamine and diethyl and triethylamine, these all have very fishy odors. And of course, by the breakdown of amino acids, these low molecular weight amines are produced. This is 1,4-butane diamine, or 1,4-diaminobutane. Okay, so we have 1,4-diaminobutane, we have 1,5-diaminopentate. All right, these have descriptive common names. This one is called putrescine. And this one is called cadaverine. Okay, these are compounds that are both given off when animals die and decay. Okay, and these are literally the odor of death. Okay, those of you that like to eat fish, you might put tartar sauce or lemon juice on your fish. Lemon juice, of course, contains citric acid. Okay, so that helps to neutralize the amines that are present in fish, and so you have a milder flavor. Tartar sauce contains vinegar, which is also a weak acid, so that again does the same thing. It counteracts the fishy flavor. Okay, there is a case where fish is soaked in brine and lye, which is sodium hydroxide, and that gives us a more powerful fishy flavor. This is a Scandinavian dish called lutefisk. Okay, that's popular in Norway and Sweden. I've never tried this, but this is one that, okay, because of how it's prepared, it has a really powerful fishy flavor and odor. Okay, I'm going to, let me pull up another tab here. Okay, I can close this. And I'm going to pull up another tab. I'm going to show you a picture here. Okay, the mouse is kind of sticking this morning. There we go. Okay, this will work, this one. Okay, I'm going to share my screen again for a minute here. Okay, there's a tree that's called the Bradford pear, and we have several of these trees on campus and around the city of Emporia. They'll bloom, I would say late March, early April. It's actually pretty early in the spring where they produce these white flowers. And some of you may have noticed the odor of the blooms. These actually produce an unpleasant odor. It's a fishy smell, and this is a result of they're producing diethylamine and triethylamine and trimethylamine primarily. Okay, so these produce these compounds, and so the flowers are not fragrant. In fact, they smell terrible. And I learned from an entomologist up at KU. His name is Chip Taylor. He's a butterfly expert, but also an authority on other insects as well. He says that the Bradford pear is, okay, because of the strong unpleasant odor that it gives off, it's actually pollinated by flies rather than by bees. Okay, there's one more thing I want to say about the basicity of amines, and that is with both over-the-counter and prescription medications. Okay, many of these will contain an amino group. Some very common examples of over-the-counter medications include Benadryl, which you take for allergies, and then Dimetap, which is a cold medicine. Okay, these both, let's see, in the case of Benadryl, that is diphenhydramine hydrochloride. So it is a hydrochloride salt. Okay, it's sold as a hydrochloride salt for two reasons. Okay, one, of course, we addressed in the slides earlier, water solubility. Okay, the hydrochloride salt will be more water soluble. Okay, the second reason is what I just talked about, and that's odor. Okay, if you had the free base, I think it would actually smell fishy. Okay, which is not something you want when you're taking something for allergies, I don't think. Same way with Dimetap. Okay, that's bromophenylramine malleate, the anion is a malleate ion. Okay, and again, that's the same. It's the same situation. The conjugate acid is more water soluble, and there's no odor, little or no odor. The amine would also be volatile, so it would, presumably evaporate or sublime. Okay, whereas amine salts are high melting, they're not volatile. Okay, if we consider cocaine, when cocaine is smuggled, it is it's converted to its hydrochloride salt, which has less odor. It's more difficult for the dogs to detect. They can usually still detect it though, but it has less of an odor. And if cocaine is then smoked, it is converted to the free base form by mixing with usually baking soda. Okay, so it's mixed with baking soda and heated, and it's smoked. It becomes more volatile when it, of course, is in the base form. The base form is called crack cocaine because supposedly when you heat it with baking soda, it produces a cracking noise. Okay, I don't know that from personal experience, but that's the origin of the term crack cocaine. Okay, so I'm going to end a few minutes early today. That concludes this chapter. I do have all of the recordings from last week posted. I was a little late doing that. So those are all up on Top Hat. And I will be providing some more online homework this week. Okay, so that's all for today. And I will see you on Wednesday.